Welcome everyone to the roof of the Forum building of the Wageningen University campus. It's a beautiful day, the sun is shining, but I'm going to talk today about floods. You've probably seen a lot of photos of flooded cities, and if you look closely then they may look the same, but they are not actually caused by the same things. So they could be caused by too high river waters, fluvial floods, or they could be caused by high sea waters if there's an ocean nearby. Those are coastal floods. But today we're going to talk about pluvial floods. Pluvial floods are caused by too much rainfall locally, so caused by heavy rainfall events that are probably going to occur more frequently in the future in many cities in the world. Rainfall events can be divided into two types. One is the stratiform rainfall. Those are the very long-lasting, low-intensity rainfall events, and they come from these blankets of clouds, low-hanging gray masses. The other type is convective rainfall, and those are very short-lived but very high-intensity rainfall events that come from cumulus clouds that are very tall and you often see them at the end of a warm summer day. And those usually cause more problems in cities than the other type. Measuring rainfall is in fact really simple. Here you have a rain gauge that you probably saw before. It's actually just a beaker in which you collect a certain amount of rainfall. Rainfall is measured in millimeters or inches. Actually, you could see that as a layer of water that's laying on the surface. 1 millimeter corresponds to 1 liter per square meter. So you can see that if you collect 1 millimeter of rainfall on a square meter, then you have 1 liter of water in your bucket. You can make these yourself as well. Just measure the surface and measure the volume of water you catch in a certain time period, and then you can divide them by each other. But of course, when it rains a lot, then it may overflow, and you have to empty it yourself. So there are also other types of rain gauges. This is a tipping bucket rain gauge. It has a funnel, so all the water is transported to the middle. And inside this thing you have a small bucket that is tipping when it's full. So if you record when it tips, you can record how much water is falling during a certain rainfall event. This is a disdrometer. A disdrometer sends a laser beam from one side to the other. And when a rainfall drop falls between it, then it will interrupt the signal and you can measure the droplet. The nice advantage is that you can not only measure how much rainfall it is, but also what type of rainfall, because it measures also the drop size and the shape of them, and also the fall speed. So you can actually distinguish between rain and hail and ice particles or snow. Of course, there's a disadvantage of rain gauges and as well as disdrometers, and that's that they're point measurements. You may be aware of an instrument that we don't have on this roof, which is a weather radar. And the weather radar sends sound signals into the sky, which is reflected by particles, so also the rain particles. And from that reflection you can derive a full image of rainfall in space, which is very valuable, of course. The last thing I want to show you here on the roof is this experimental setup. You may recognize this thing as a thing that you usually see on the towers that are used for mobile telecommunication. There's another one of that on a building 2 kilometers that way, and it sends a signal to this one, just like it would have when it would be still on a tower for telecommunication. The rainfall will hamper that signal, and that's very annoying for the mobile phoning companies, but for us it's actually useful because we can derive rainfall from it. This is of course a very useful treat for urban purposes, because where many people are a high population density, of course the density of these type of links are also very high, so you can get a very detailed map of rainfall intensities. And this is an experimental setup where we have different kinds of links to test which ones are best. This is all I wanted to show you on the roof. For the next part, I want to show what happens when the rain hits the ground, and for that I'm going to take you to a rainfall simulator. So as I promised, I would show you what would happen when the water hits the ground, but as you see it wasn't raining outside, so I have to go inside to make it rain. And that's why we're here. This is the Laboratory for Water and Sediment Dynamics, and here we can simulate all sorts of water flow. So mostly in river reaches where we can see how the water and the sediments on the bottom of the river move. But we also have a rainfall simulator, and that's where we are now. I made a little experiment here in the rainfall simulator. I have 3 buckets of soil. The first one is with a little bit of grass inside. It's an unpaved surface, which we can see in parks or in rural areas. And there's just soil and grass on top, and all the water that will not infiltrate can flow off and be caught in that beaker. The second one is a rooftop material. So this illustrates the paved surfaces in the city. And the last one is a semi-paved area where there are rocks, but there's also soil beneath. So I just turned on the rainfall simulator, and this is a light rainfall event. You can see that on the grass, the droplets are just laying there, whereas on the paved surfaces, they're really starting to run off. That's because the leaves of the grass intercepts the rainfall. As long as the column is not completely saturated, if there's still space in the soil, the water will be taken up by the soil and you won't get as much runoff as at paved surfaces or semi-paved surfaces. So we just had a very light rainfall event, and you can see that in the place where the grass is situated, there's hardly any rainfall measured because the rainfall intensity is lower than the infiltration capacity. As long as the column is not saturated, water will keep flowing, will keep infiltrating. That's not the case at the paved surface, where you can see that a lot of water has run off the surface and not that much water will infiltrate into the soil because it's sealed. And the last one is an intermediate case where you have some water captured, but not as much as in the paved one. So now we're going to see what will happen when there's a more intense rainfall event. You can see that the rainfall intensity is much higher, like a convective rainstorm. And also in the case where there was, in the grass case, you can see clearly runoff now because the rainfall intensity is now higher than the infiltration capacity. So the rain has stopped, and now we can look at the results. As you can see, the least water has been caught by the grassy bucket. That's because not all water is flowing off the surface, but most of it is infiltrating into the soil. You can illustrate this with a sponge. The soil really acts like a buffer. So the rainfall that is falling on an unpaved surface will be delayed, so it's much easier in your sewage systems than, for example, this paved surface where most of the water is running off. And you have very high discharge peaks, very high peaks of flow into your sewage system. And of course, the semi-paved one is, again, an intermediate case. So here you can see that rainfall intensity and also land cover are really linked in determining whether pluvial floods occur or not. So heavy rainfall events, which are probably going to occur more often in the future due to climate change in many places in the world, can cause pluvial floods, which is especially a problem in areas with a lot of paved surfaces, like in the cities.